What is the call stack's mechanism for return addresses? Imagine you're reading a book and every time you finish a chapter, you flip back to the page where the story paused. That's similar to how the call stack manages return addresses in programming. When a program runs, it often calls functions, which are like mini programs within the main one. The call stack keeps track of where to go back after each function finishes. Here's how it works. When a function is called, the computer saves the address of the next instruction to run after the function ends. This address is called the return address. The call stack stores this return address by pushing it onto itself. Think of it like stacking a new card with the return address on top of the previous ones. Once the return address is saved, the program jumps to the called function and starts executing its code. When that function is done, it needs to return to where it was called from. The program pops the top return address off the call stack, which means removing it from the top. Then it updates the program counter, which is like the instruction pointer, with this return address. This tells the program exactly where to continue from, resuming the previous task seamlessly. This push and pop process happens every time a function is called and finished. The call stack operates in a last-in, first-out manner. That means the most recent return address added is the first one to be used when returning. This system keeps track of nested function calls, even if one function calls another, which calls yet another. For debugging, understanding this process is key. The call stack shows the sequence of function calls that led to the current point in the program. When a bug occurs, looking at the call stack reveals the path the program took and helps identify where things went wrong. Each frame in the call stack contains the return address, along with other data like function parameters and local variables. Different computer architectures might organize these frames differently, but the core idea remains the same. Some modern processors even use special hardware to predict return addresses for faster execution, but that's transparent to programmers and debuggers. Complex control flows like exceptions or threading can make managing return addresses trickier, but the fundamental concept stays consistent. When you examine the call stack during debugging, each frame shows a function call and the return address pointing back to the caller. By stepping through these frames, you can trace the execution path and find the source of errors. Mastering how the call stack handles return addresses helps you interpret stack traces accurately and fix bugs more effectively.